just alone today. So today it's going to be about differential geometry, and I want to finish the lecture today. So I will try to be a little bit quick here. Okay, so what we've seen so far for representing data is mostly vector spaces, and not everything acts as a vector space. And what we're going to see today is manifolds, which are a space where the axioms of vector spaces usually don't apply, either because we are talking about a subset of the vector space where basically we don't have closure, or we are talking about some completely different structures. But there are manifolds actually found everywhere. So if you think about the Earth surface, this is the most famous manifold. It's a curved space, and it's not a manifold. It doesn't. The surface of a sphere breaks this axiom of closure. There's the robot configuration space. The parameters of a neural networks also make a manifold. And when we define optimal behavior, we want to have the right representation. So I talked about this a little bit, I think, in the differential equation lectures, that representations of the problem is very important in order to design algorithms. And so, yeah, if we understand the geometry of the problem, this leads to what we call covariant algorithms or intrinsic algorithms, meaning that the parameterization of the problem, or if we move on to another problem with a different kind of parameterization, and we apply the same algorithm, the algorithm carries out really well. So what we'll talk about today is, well, I will introduce what manifolds are. We'll talk about tangent spaces and how to characterize the tangent space to a manifold. And then we'll talk about something called Romanian metrics. And we'll see that the characterization of a manifold can happen either intrinsically or extrinsically. Extrinsically means that it has to do with the embedding. So how is the manifold actually embedded in some higher dimensional Euclidean space? But also intrinsically through the Romanian metric. And this is called the Nash embedding theorem. And I will hopefully give an intuition about what that is. So if we look at the Waymo driver, as usual, we have the Cartesian space is itself a manifold, even though it's a vector space. The position and orientation of the car SE2 is a manifold. That's not a vector space. The velocity and moment are actually part of the tangent space of SE2. And this notation that we have here we'll introduce next week in the Lie group lecture. This is actually the notation for the Lie algebra, which is the tangent space of the manifold at the origin. The configuration space is also a manifold. I said this for the robot. So if robots have multiple joints, the product of their joints makes a space that's the configuration space, and it's actually a manifold. And yeah, so any model that is characterized by a set of parameters in machine learning will also produce. So the space of models will produce a manifold, or is a manifold. Okay, so what we're going to talk about today. First, we're going to see why geometry matters at all, and by a set of examples, briefly, and then we'll introduce differential manifolds, and then Romanian manifolds. Okay, so why does geometry matter? So if we look at the sphere, so here we have a straight line on the sphere, drawn on the sphere, and we have the same straight line in red drawn on the common map. And what we see is that the actually true shortest path between here, it's New York and Tokyo, is not the straight line on the common map, but rather something that bends in a particular way. And that bending here has to do with the actual geometry of the sphere, which is not well represented on the common map. So the sphere is actually a manifold, and its definition is the following. It's SE2. So S2, the sphere, the surface of the sphere, is any point in 3D Euclidean space whose dot product, so whose square norm, is equal to 1. Or norm equivalently is equal to 1. And that defines the surface of the sphere, and that defines actually the manifold that we call the sphere. So there are many maps for the surface of the Earth, and all of those are kind of valid representation of the surface of the sphere or of the Earth. It turns out that we are more familiar with this one, but it's they all have to do with a different stretching of the actual surface in order to put them on the plane. And of course, one that would be valid is the one that would stretch minimally the map. And we see that some of them, for example, here there are spots or points on the map that are highly warped. And so they're not actually equivalent, but they're all valid. Okay, so let's take an example where geometry would matter in a machine learning problem. So we have the original data here, which is in three-dimensional space, and it makes this kind of Swiss roll here. And the closeness, so they are associated with a scalar value, which is the color, and they are close in Euclidean space, in their embedded space. And we want to perform some dimensionality reduction and then make a decision based on that two-dimensional representation. So this is the original data. This is the projected data through phi. And so the data lies on some embedded nonlinear manifold. So this is the actual Swiss roll is a manifold, and it's a nonlinear manifold. So the machine learning problem here would be to find this Euclidean, this embedding in Euclidean space, which is here, that minimally distorts the metric, and where we have the embedding that is nonlinear, but the metric in feature space would be linear. So you see that if we had to then predict what would be the color based on some dimension of the features, which are Euclidean. So here you see that on the x-axis, we completely predict what would be the color, where here the x, y, and z-axis do not predict the color at all. Okay, so that was for learning the manifold, learning a Euclidean embedding for the manifold. But what about when we have a problem which itself has an intrinsic geometry, and we can use that geometry because we are designing the algorithm from the standpoint of having access to the full problem. So this is the case in robotics, where we know that we have a certain geometry linked to the robot kinematics, and that geometry will yield certain representations where we would perform learning or control that are much better suited at representing the actual problem that we want to solve. So this is so the first one here on the left side is the manifold of unit quaternions, and so it's S3. So we saw S2 where it's the points in 3D Euclidean space whose norm with respect to the origin or whose norm are 1. And here it's in four-dimensional space where the norm is 1. So that's actually the manifold of unit quaternions. And they can be used to represent three-dimensional orientations of a robot end effector. And this is the actual natural kind of representation for the orientation. S3, actually we also use SO3, and we can map from S3 to SO3 quite easily. But both of those are manifolds, and they have a specific geometry. For what what we call manipulability ellipsoid, we can use the space of semi-definite or positive definite matrices, which are, so here for S6, which are squared matrices of size 6 by 6, and they have the property of being symmetric and being positive definite. So here I put the definition of positive definiteness. It means that if we compute the norm with respect to x as a metric, it will always be positive and never negative. So yeah, so this is the manifold of symmetric positive definite matrices and can be used to represent what we call in robotics manipulability ellipsoids. And so these are positive definite matrices which express the capability in translation and rotation that the robot has for a particular configuration. So it has the structure of a cone, and so all the positive definite matrices have to be within inside this cone, and the shortest distances, which we'll see at the end of the lecture, what's called the Geodesics, are these little lines, these curved lines that are represented here. And here on the left side, we have the surface of a sphere, and same thing, so the points on the manifold are on the surface of the sphere, and the shortest paths between the different points of the manifold are these curved lines. Okay, so this was to introduce why geometry may matter and how it's kind of used. So let's define a differential manifold. So what is a manifold? So a manifold is some kind of smooth, not necessarily smooth, but continuous thing where we can interpolate between the points, and it is locally, it resembles Euclidean space. It's not, as I said, it's not a vector space. It doesn't obey closure, the closure axiom of a vector space, but locally it looks as if it's a Euclidean space. So the example that we have here is the circle. The circle is itself, it's called S1, is itself a manifold, and you can see that if we take local patches of the circle, we can kind of assimilate it to a line, and this is what it means to be locally Euclidean. So more formally, an n-dimensional manifold is a topological space which is locally Euclidean, which means that it can be covered with a set of homeomorphisms. These homeomorphisms are called here phi, and they map some little domain of the manifold, which is called U here, to some subset of Euclidean space, or N. And N is the dimensionality of the manifold. Whoa. Hey. Oh, this is strange. Okay. So, so what is a topological space? So it's a set with a neighborhood for each element. I won't go into details about what that is, but that's it. So if you have a set and each element within that set, I can extract what its neighborhood is, which is, for example, the case of Euclidean space. Euclidean space is continuous, so it has an infinite number of points, and if I take any point in Euclidean space, I can kind of see what the neighborhood of that is. But a topological space does not need to be continuous, it can be discrete, but you have to have this neighborhood structure on it. In the case of manifolds, actually, we usually require that the topological space is continuous. And so a homeomorphism is a function that maps some set X to some set Y between two topological spaces. That is a bijection, so meaning it's a one-to-one and onto mapping. It is continuous, and it has an inverse function that is also continuous. Okay, so that the intuitive definition of a manifold is that it looks locally like Euclidean space, and the more formal definition here is to say that it's associated with a set of charts, like we have as an example for the circle, that maps like some local patch of the manifold to some Euclidean space through a homomorphism. So then the second question would be, what is a smooth manifold? So a smooth manifold is something that includes transition maps, which means that there's a non-zero or non-empty intersection between the different patches which are homeomorphic to Euclidean space. So here in this depiction, you have a first chart phi, which maps a patch of the manifold to some subset of Euclidean space U hat 1, and then you have a second one that maps to U hat 2, and they have some intersection here. And the transition map is basically the intersection on the manifold together with phi and the inverse of the map, psi and the inverse of the map phi, and that will map to U hat 1. Oh, yeah. U hat 2, sorry. Okay, so an atlas is a collection of coordinate charts. So it's all the charts that are necessary to fully cover the manifold. And an atlas is called smooth if there exists a transition map, or if there exists a transition map, between all its charts. So transition maps operate a change of coordinates, which means that there are diffeomorphisms between subsets of Euclidean space. So a smooth manifold, I will come back to what a diffeomorphism is in a second. A smooth manifold, M, A, is a manifold with a smooth atlas. So what is a diffeomorphism? So the basic intuition is that it's some kind of warping of the space itself. So here we have a diffeomorphism from R2 to R2. And if we consider a differentiable map F, which operates this kind of warping between two manifolds, M and N, it will be called a diffeomorphism if it is a bijection, 1 to 1 and onto, just as the homeomorphisms. But the additional constraint is that its inverse is actually differentiable. And now we have the inverse function theorem, which says that a differentiable map, F, is invertible, is equivalent to saying that the determinant of the Jacobian of F does not vanish on the domain. Okay, so all right, so yeah, so if we have a diffeomorphism, it means that for our transition map, I come back here. It means, yeah, so we have a change of coordinate, meaning that when we are in this intersection, we can represent the points on the manifold using their coordinates in one chart or the other chart within that transition map. It does not matter. We can just completely smoothly change the coordinates. Either we use the coordinate in one chart or the coordinates in another chart. It does not matter. That's what this diffeomorphism property means. Okay. Let's take, just to give more intuition about what these charts are, let's take some examples. This was not supposed to show like this. Okay. let's take some examples of global charts. So first we have the Euclidean space, which itself is a vector space. So it has the property of closure, but it also has the structure of a manifold. So a global chart for the Euclidean space is simply going to be the identity. So that's easy to understand. So the mapping to a Euclidean space for that particular Euclidean space, of course, is the identity. Another type of manifold is a parametric smooth surface, which basically takes in a subset of Euclidean space and through its inverse function generates the points of the manifold. So the chart here will simply be F itself. So F defines the manifold, but F is also the chart here. Okay, so in the example that we have here on the right side, the manifold is actually the surface defined by F. Okay? And if I want to index through Euclidean space, if I want coordinates that are Euclidean vectors in that curved space, in the surface, I will look at the coordinates on the plane in R2, and that will index the points that are on the surface. Okay? So F here is a function I think I had a problem with this example because F is simply here the restriction. Well, come back to that later. Okay. Another example is the space of Gaussian distributions, and here a chart would be the mean and the variance or the covariance associated to the Gaussian distribution, and so the mean would be a vector in Rn, and the covariance would be a positive definite matrix. So let's take the example of the Gaussian distribution and see what the transition map would be here. So Gaussian distribution of mean 0 is simply defined by the standard deviation here. So here we have 1 standard deviation, and then 2 and 3 and so on. So the space of Gaussian distribution is parameterized by the mean and standard deviation, but it can also be parameterized by the mean and the variance, meaning the square of the standard deviation. So a smooth reparameterization or a change of coordinates, or like going through two global equivalent charts, would be a chart that just squares the variance here. Now, let's take the example of the sphere again. So the sphere actually cannot be represented by a single chart. It has to be represented by at least two charts. And the kind of classic charts, so there are many multiple ways we can have charts for the sphere. So remember, the Euclidean space that we have to map the local patches of the manifold to has to be the same dimension of the manifold as the manifold. So the sphere is embedded in three-dimensional Euclidean space, and we are talking about the surface of the sphere. And the surface of the sphere is, of course, two-dimensional. So the kind of classic way to generate a chart for the sphere is called a stereographic projection. And it's basically projecting all the surface of the sphere back onto the plane that is associated with the south pole. And then you can make another one of these charts which generates it for the north pole. And yeah, so that's in general the case that for manifolds we need multiple charts to represent or to fully map the manifold. And so for the surface of the sphere, as I said, it cannot be covered by a global chart. And with stereographic projection, we have the north pole that leads to, that's the following mapping for the north pole. So it takes X and Y associated with the circle here, and then Z associated with the height along this axis here, and generates these big circles here. So an atlas for the sphere would be this one and the one for the south pole. The north pole, sorry. The south pole, yes. Okay. So let's take now the example of submanifolds of Euclidean space. It's maybe the most common form of manifolds. And yeah, so there are subspaces of Euclidean space. And they are kind of defined as a kernel of a nonlinear smooth map. I'll see that in a second. So, for example, we can define the unit sphere in dimension n as an implicit surface using the following function. So you just take the norm of the vector in the Euclidean space, and you subtract it to 1, and you make that equal to 0. That's what I mean by the kind of kernel of the map F. And so the definition of a submanifold of Euclidean space would be that it's defined such that if we define a smooth nonlinear map, the manifold can be expressed in the following way. It's the inverse image of 0, so all the points who have 0 image through F. And then the dimension of the manifold will be m minus n. So in the case of the sphere, n is 1, because that's the function here. And so the dimension associated to the manifold is going to be whatever the Euclidean space that we're considering for the hypersphere, minus 1, which is the dimension here of the image of F. So F and F inverse do not provide valid charts for M here. So I put as a note that there are other classic manifolds that can be defined as implicit surfaces or hyperplane and the torus, and these are so the hyperplane or the torus, so these are these classic manifolds that can be represented in the same way. Okay, just a side note on product manifolds. If we have multiple manifolds, then their product is going to also be a manifold. So here we have the cylinder or the torus can be represented as the product of simpler manifolds. And the resulting chart is the product of the chart as well. Yeah. Okay, so now, going quite fast actually today. So the next thing we want to introduce is tangent vectors and tangent spaces. So as I said, so the one way to see what a manifold is that it's some kind of topological space, so something with neighborhoods that locally resembles Euclidean space. And smooth manifolds can actually be differentiated along. and what is the elements, so how we transition from, so one way to intuitively see this is kind of like the surface of the sphere. It has, if we move along the surface of the sphere, we are following a direction that would always, if we really totally follow that direction, make us fall outside of the surface of the sphere. So the direction that we are following on the surface of the sphere belongs to something called the tangent space of the sphere, or the tangent plane, if we're thinking about the two-sphere. And so for general abstract manifolds, we want to define exactly what a tangent vector is. So the basic intuition is that tangent vectors indicate a direction on the manifold. And to specify a tangent vector, we can specify a curve on the manifold that we are following, and then take the derivative of the curve at the point P on the manifold. So here you have the depiction, and you have a point P, which is this green dot here. And then if you follow that curve on the manifold, that point P is associated with a direction of kind of motion, of movement on the manifold, and that is a tangent vector. Okay? So there are multiple ways to define properly tangent vectors, and we're just going to see one today. But maybe let's come to a simpler case, the case of a curve in two-dimensional space. So we can define a coordinate system here for the embedding space, which is the two-dimensional space. So we have an x coordinate and a y coordinate, and the manifold is this curve, this red curve here. And so if we are at any point along this curve, we can define the tangent line, and that would be the associated tangent space to the one-dimensional manifold. And the tangent curves, the tangent to a curve like that is simply given by the derivative of the curve itself. So if we remember from 3 weeks ago how we can get the first order Taylor expansion of a curve, which associates a point on the curve to this kind of tangent line here. We have the coordinates of that line that associates, it's an affine line that associates a coefficient, direction coefficient, and then an offset with respect to y here. So curves in R2 obey the definition of manifolds as implicit surfaces that we just saw. So we have a function that I called here G, which defines kind of a constraint, and so the curve is embedded in two-dimensional Euclidean space, and it's all the points that obey that constraint. G of P is equal to 0, and P is part of the embedding space. And what is G exactly? It's the function that associates to P. P has two dimensions, x and y, the function f of x minus y. So when f of x minus y is equal to 0, it means that we are along that manifold line. Okay? And so the tangent space, or the tangent space to any point along that curve is going to be that affine line definition that we saw here. So that's just for the 1D curve, very trivial example. If we now want to define in an abstract way what a tangent vector is, well, we cannot differentiate like that on an abstract manifold. Okay, that is because tangent spaces are not. If we take two tangent vectors that are neighboring, they are not part of the same tangent space, and so we actually don't have, as I said, closure on the manifold. It's not a vector space, and so we cannot subtract vectors from these spaces. So we cannot really actually points on the manifold that are neighboring. We cannot we don't have closure on the manifold, and so we cannot define the derivative there in this way. So the way that we define properly and formally tangent vectors is a little bit complicated, and I don't want to get so much into it. But the basic idea is that we associate to the manifold a function f that maps points on the manifold to a real number, and then we differentiate that function, and that gives us the definition of what a tangent manifold is. So if we have a function that maps the manifold to a real number, and that function is smooth, then there exists a curve gamma on that manifold for which gamma at 0, so gamma is over the interval -1 and 1, let's say, that satisfies the following. So if I compute the time derivative of f at that point, gamma t, which is a point on the manifold for t is equal to 0, and I derive the function here, then a tangent vector is going to be something that associates f to, is an association between that function f and the manifold itself at that point 0. And that's what the tangent vector is. So yeah, so that's a little bit abstract, and I will stop there, but you have to understand the intuitiveness behind it, so we cannot directly differentiate on the manifold. That's why we go through this abstract definition of a manifold, of a tangent vector, sorry. And we introduce this this function f, which we can differentiate. Okay. So then what is the tangent space? Well, it's the set of all the tangent vectors. So just as we did for vector spaces, we define the axioms of vector spaces such that we could define vectors, and then we define vector spaces as the collection of vectors. We define it the other way for vector spaces. We define the axioms for a vector space, and then vectors were the element of the vector space. Here it's different. We define tangent vectors, and tangent spaces are going to be the collection of tangent vectors at a point. And the tangent space has actually a vector space structure, which means that the tangent vectors can be linearly combined to produce other tangent vectors at that particular point. And this is kind of how you see it. Okay, so this is for the abstract notion of a tangent vector. You can look at it more closely to understand it. And the abstract notion of a tangent space, which is always going to be a vector space. And so that's great, because now we can apply all sorts of calculations on the tangent vectors, which we could not do on the manifold itself. So we could not, So let's go back to something that we can understand, which are tangent vectors on submanifolds of vector spaces. So as I said, if you take a subset of a vector space, like it's the case for the surface of the sphere, it's itself a subset of a vector space, you break the axiom of closure, so you're not in a vector space anymore. But if we consider that case of tangent vectors of submanifold of subvector space, we kind of simplify the idea, because how we define the tangent spaces is going to be more straightforward. So yeah, so generally a tangent vector is something, to a submanifold of a vector space, something that can be seen as an arrow in the tangent space of tangent to the manifold. And so when M, the manifold, is defined as the level set of a constant rank function, which was the case with these implicit with this curve in two-dimensional Euclidean space or on the surface of the sphere, we have that the tangent space is defined as the kernel of the time derivative of f, which is the defining function in an implicit surface, for instance. So that's going to define all the set of vectors that are tangent to the manifold at a certain point P. So let's see the example of rotation matrices. So rotation matrices is the special orthogonal group of dimensional 3, and they are just squared matrices. Remember that the space of matrices is a vector space, and we talked about this, how matrices has, squared matrices or matrices in general have a vector space structure because you can scale them by multiplication with a scalar element-wise, or you can add them in the case of rectangular matrices. That's the vector space structure of rectangular matrices. But for squared matrices, you can also multiply them. And when we talk about so here that's all we care. So we can add them. It also, SO3 also has a group structure through, through the multiplication, SO3 is also, SO3 is also a vector space through multiplication, right? Where multiplication, but then it's part of the general linear group. It's a subspace of the general linear. Well, anyways, my point is not to see what's the vector space structure of SO3. My point is to here try to see what is the tangent space of SO3. So we can first derive the function f. So here the function f is RTR is equal to the identity. And we can derive that. So we first have to make RT depend on time. Then we derive with respect to time. And what we get through the product rule is that line here. So R dot transpose R plus R transpose R dot. And that gives us the structure of the tangent space of SO3. Yeah, I think so. Here, the underlying vector space has to do with addition. We don't care whether it has a vector space structure with multiplication. Right? Anyway, so this is the tangent space of SO3, where we care about the element of the tangent space are going to be these R dots, right? And so here they are associated with 3 by 3 matrices, which are constrained in the following way. We will see next week, because SO3 is also a Lie group, we will see a Lie group is just the extension of a manifold to our manifolds that also obey the group axioms. And yeah, so we will see this next week. But the key idea here is that the element of the tangent space of SO3 are skewed matrices, and because that's the definition of a skewed matrix here. We'll see that next week. Okay, so manifold are these kind of curved spaces that don't obey the axioms of vector space. I've said this many times by now. And the key idea of Romanian manifolds is that we want to be able to compute what should be kind of the shortest path between 2 points. And so the way we can do that is by associating to the tangent space of the manifold an inner product that is going to vary smoothly along the manifold. So that means that at any given point on the manifold, we could be going at any direction, or the directions that are given by the tangent space. Remember that the tangent vectors come from the derivative of the kind of underlying manifold structure, which when it's embedded in Euclidean space, we can simply do what we did, which is we take the function that defines the constraint surface, and then we differentiate that surface here, and that derivative of that function gives us what is the tangent space at that particular point. But it prescribes all the directions that are possible. So for example, if you're on the surface of the sphere, there's a tangent space here, and these are all the possible directions that you might be going, but you see that you will be going on a plane. On the two sphere, you'll actually be going on a plane, but there are 3 kind of 60 directions that you could be moving into. Now, the idea of the Romanian metric is telling you, well, so how the space is kind of locally curved. And so how some of these directions will make you move more or less than others. That's the notion of the Romanian metric. It's an inner space, structure on the tangent space. Yeah. Oh, sorry. Don't understand what's going on here. Sorry, something went wrong here. Missing item. What? Ah, come on. What? I don't hear. Yeah, but now it worked. So the PDF is in Ilias. Yeah. Okay, so in coordinates, this corresponds to a smooth family of positive definite matrices. As we saw, like an inner product, proper structure of an inner product in coordinates is always associated with a positive definite matrix. And yeah, so this is what's written there. That's the Romanian metric. Okay, so an example of a Romanian metric, for example, in Euclidean space, going to simply be the identity. It's constant and equal, and just defines the inner product between two tangent vectors. The tangent space of the Euclidean space is the Euclidean space itself, and so the inner product between two vectors from Euclidean space is going to be simply the dot product. And so the associated Romanian metric is simply going to be the identity. Now, if we go back to the sphere itself, the surface of the sphere, if we want to do calculus on the surface of the sphere, it's not as simple as doing calculus in Euclidean space. So one way to do that, of course, is to use a coordinate chart. So remember, it's a thing that maps to basically what we saw in the beginning, these charts of the Earth, right? So that maps to a two-dimensional space, which is the surface itself. And the way we can do that is we take the three-dimensional positions of the points on the surface, and we map them to their phi and theta coordinates that are associated. So the theta coordinate is going to be these are polar coordinates, so associated with what is the rotation along a particular axis along the plane. And phi is going to be the azimuth, kind of like what is the elevation associated to the point on the surface. So if we now, we want to do calculus with respect to these surface elements. So if we want to look at the line element, so here I depicted what is theta, right? So theta is this angle along the kind of planar location. So for the Earth, these are actually the coordinates that we use, longitudinal and, yeah, I don't remember exactly the geolocation kind of things. So the line element is going to be this diagonal element of this little square here. And so I noted the different things here. So we have d theta is this element, d phi is this element. And if we want to compute what is the diagonal here, the arc element is going to be, so in Euclidean space, in the embedded space, this would be ds squared on the surface is going to be dx squared plus dy squared. Of course, if you take the root of that, right, you get the diagonal. That's just the idea of Euclidean distances here. And so if I now identify dx squared with the phi element, I just take d phi because it's directly proportional to the angle phi here. And if I want this element, this is more complicated because it's associated to the distance to the z-axis, which is sine phi times the little angle here d theta. Okay, so sine phi times d theta is going to be that line element here. And now I have what is the actual diagonal of that squared element on the sphere with respect to the chart's coordinates. So on the surface of the sphere, where it's a unit sphere where r is equal to 1, so we don't take into account actually this distance here. I mean, we do, but it's just 1. So a curve gamma t defined in that chart, theta and phi, on the sphere will have the following length. So we will integrate these little line elements all the way on the sphere between the two coordinates along that sphere. That's just the formula for calculating the length of a curve on the sphere. Now, I want to introduce something called a pullback metric, which is, and we'll come back to the sphere in a second, which is the thing that we get if we map the tangent space elements to some other tangent space of some other manifold, and then we get that Romanian metric from that tangent space and measure the difference between tangent vectors with respect to that metric here. This is called the pullback metric. So formally, if we have M and N that are two differentiable manifolds, and F is a differentiable map between these two differentiable manifolds, then the pullback pullback from N to M along of the metric defined in N along F is a quadric form, meaning what we saw before, so this inner product on the tangent space of M, such that it obeys the following formula, meaning that it's the mapping of the tangent vectors V and W through the differential F. So V and W are elements of the tangent space of M. That's written here. And df is something called the push forward, but it's basically just the derivative of that function that maps from F to M. And in coordinates, the product on the manifold N has a matrix form, and so the pullback metric has the following form. It's the form J, where J is the Jacobian of the map F, times AN, where AN is the matrix form of the inner product on the tangent space of N, times JF again. Okay? So that's the pullback metric. And now we're going to come back to the sphere. And before that, we introduce the induced metric. The induced metric for some manifold M embedded in some manifold N results from the restriction of the metric defined on N to M. And so if we have a mapping from manifold M to manifold N, which defines some embedding, then, and if it is an injective homeomorphism, it has a continuous inverse. So for the example of a submanifold of Euclidean space, we have that the function so our embedding here maps from Euclidean space to Euclidean space. The push forward here is the thing that, the derivative, so the thing that maps tangent element to tangent element on the other Euclidean space. And so the induced metric by the embedding being F, is simply the pullback of the identity metric because of what we saw just before. So we are mapping to we are embedded in Euclidean space, and then we are measuring inner product on that on our tangent space, our manifold M here, with respect to the metric on the tangent space of N. And there, how we measure things is by the identity, is because it has a Euclidean metric, and we pull back that Euclidean metric, and so the metric on induced on M is going to be the Jacobian of F transpose the Jacobian of F again. Okay? So now we come back to our sphere. Our sphere is embedded in Euclidean space of dimension 3. And we want to, it has a natural metric which comes from the embedding, which I explained kind of informally by how do we compute the arc length on the sphere. We compute the arc length on the sphere by seeing what is the kind of Euclidean way of computing distances in the embedding space, and then using that in our chart. Another way to see that is to say, through the induced metric, is to say our sphere is embedded in Euclidean space through the mapping F that we saw before, which is simply 1 minus the norm of the point here. And then we define a specific chart. So it's the embedding is actually the chart itself. So we pull back the metric from the Euclidean space through the chart. So it's embedded in R3, and we have coordinates charts as defined before, where for any points on the manifold in 3-dimensional point, we can extract a 2-dimensional coordinate phi and theta by these angles that they make with the plane and the angles that they make for the height here. So this is actually an injective homeomorphism, meaning an embedding, to a subset of R3. So it has an inverse, right? And so typical chart is taking 3-dimensional points on the manifold, mapping them to a Euclidean space in a homomorphic way. That's the definition of a chart. And it has an inverse in this case, and the inverse takes the coordinates and maps them back onto the manifold. And so this is what this is here. And we can compute the induced metric by pullback of the metric in R3. Here, simply the identity. And the procedure to compute that metric is just to compute Jacobian transpose F times Jacobian of F. Okay, so let's do that. So the Jacobian of the embedding function is the following. So we derive the first coordinate and the second coordinate and the third coordinate. Oh, these are not the coordinates, but these are, well, these are the points on the manifold. The coordinates with respect to, the first coordinate in the chart and the second coordinate in the chart. So this gives us 3x2 matrix. You can check that with respect to this function f, we actually get these things here. And now we compute the product between the transpose of the Jacobian and Jacobian itself of f. And if we use the sine and cosine identities, the following ones here, we get the 2x2 matrix, which allows us to compute these Euclidean distances on the surface of the sphere with respect to tangent vectors. So let's go back. So here we have our Romanian metric. in that particular chart, right? That particular f that we took. And here you see that the way that we measure distances on the sphere with respect to the Euclidean distance is exactly what we found by pulling back the identity using through that mapping. Okay? This is called a round metric. Okay, so we saw that we could compute the Romanian metric associated with the surface of the sphere by pulling it back from the natural embedding of the sphere, the three-dimensional Euclidean space. And the Nash embedding theorem is answering the question to whether every kind of manifold in every high-dimensional crazy space can be embedded in Euclidean space, meaning that we can recover the local curvature, so how to measure distances. So distances on the manifold, like along a curve, is the integral of the So how we measure distances along the curve is by computing the norm of the tangent vectors, right? Yeah. And so if we can find a tensor, a Romanian metric, that so this is the difference between intrinsic and extrinsic definition of the manifold. The manifold is fully defined, so that, well, it depends actually, but so when we say that the manifold is intrinsically defined, it means that it's fully defined by the Romanian metric itself, meaning that we can compute distances on the manifold simply by looking at the Romanian metric tensor. And what it does is it gives us a way to compute length of curves on the manifold locally, purely based on the metric tensor. And the Nash embedding theorem is answering the question of whether we can always define that metric tensor using some embedding into some Euclidean space where the metric is Euclidean, meaning the tensor is actually just the identity, and so the metric tensor on the original manifold is fully only defined by its embedding f. So for surfaces in three-dimensional space, it has a nice, we can visualize these things quite nicely. It simply means, can we embed the surface in Euclidean space? But for higher dimensional spaces, it's much more complicated. And then the embedding is not some natural thing that we can visualize or conceptualize easily. But basically, the theorems cannot show that it's always possible under some constraints that have to do with the dimensionality of the embedding function. Okay, so the last thing is to actually define what are shortest paths on the manifold. So on the sphere, that's the notion of geodesic. On the sphere, the geodesics are called the great circles. And if I take these A, B, and C points here, I define what I call, or what is called a geodesic triangle on the sphere. And you can see that it's not really a triangle, it's kind of bent, right? But it's the equivalent of a triangle, but on a curved space. And the great circles are the equivalent of of straight lines on the curved space. And the way that they are defined is by being curves that minimize the this delta operator, or nabla operator, where nabla is equal to 0. Nabla is actually called an affine connection in Romanian manifolds. And I don't want to get into how you define these things, but basically an affine connection or connection in general is a way to differentiate tangent vectors. So it's a curve for which along the curve there's basically no acceleration, or it's orthogonal to the tangent vector, the tangent space, sorry. And the geodesic generalizes the notion of a straight line. So, yeah, so the key idea is that the geodesic between 2 points locally minimizes what is called the length functional, and it's the idea that we measure length by taking the Romanian metric at the point gamma t and measuring the inner product between the tangent vector. So we measure the norm of the tangent vector with respect to that Romanian metric on the tangent space. And we want to minimize that across the curve gamma. Okay? So just to come back to the Nash embedding theorem and all that stuff, the idea is to say between the intrinsic and extrinsic definition of a manifold is to say that we can always define G, which is the inner product structure on the manifold, by its embedding in Euclidean space, by an embedding in Euclidean space, F, in a higher dimensional Euclidean space, such that it defines the notion of distance on the manifold between 2 points. So basically, the embedding kind of will define curvature on the manifold. So if you have the sphere, what defines the curvature of the sphere is its embedding in 3-dimensional space. So we can define that curvature fully through the embedding, which leads to a Romanian metric, which leads to a notion of distances on the manifold. And that is regardless of what is the kind of structure of the manifold, the dimensionality of the manifold, or whatever. There's always a Euclidean space in which it can be embedded. But that Euclidean space can be of very high dimensions. Okay, so the solution of this energy functional is the geodesic equation. It's actually, the geodesic equation is the Euler-Lagrange equation of the length functional. And you see that there's this, it's an ordinary differential equation of order 2. These are on the chart coordinates. And this gamma thing here is called the Christoffel symbols, which characterize the connection. So the thing that allows us to differentiate between different tangent spaces. And for Riemannian manifolds, so ones that are characterized with a proper inner product structure on their tangent spaces, there's one connection that minimizes the torsion, that has no torsion, and that preserves the metric. That's called the Leavitt-Civita connection. I said I didn't want to get into the connection thing, but just to give you an idea, the connection is fully characterized by the metric tensor, the Riemannian metric tensor, actually the derivative of the Riemannian metric tensor. So the geodesic equation, being this second-order differential equation, means that if you are at a particular point on the manifold, and you start at with a certain direction, with a certain magnitude, you will follow a curve. Like if you're on the sphere, for example, and I start with a certain velocity in a certain direction, I will follow a curve. That curve is going to be a great circle and come back to the point itself, no matter what. If there's no friction or anything, and that curve that I'm following here is fully defined by the geodesic equation. Okay. What we're going to see next week in the Lie group, or not next week, the next lecture, in the Lie group lecture is a certain number of closed form formulas for differentiable manifolds that are also groups. So especially we're going to focus on some kind of sphere groups, and so the group of quaternions, and we're going to focus also on SO3, so matrix groups, where there are closed form solutions for the length between points on the manifold. So basically, if I start at a point on the manifold, and I start in a particular direction, and I want to know exactly where I will arrive after time t, if I start with a particular tangent vector, there's a closed form solution that will tell me exactly where the geodesic will lead me. These are the solution of these, actually closed form solution to the geodesic equation. And and that's it. There's also something that I didn't talk about today, which is the parallel transport of vectors on the tangent space. So if I have a vector on the tangent space, and I want to move that vector on the tangent space to another point on the manifold, but I want to keep the vector kind of parallel to the surface, there are also closed form solutions for manifolds, for like classic manifold like the sphere and so on, that will tell me exactly how the vector should be transported to another tangent vector, tangent space, and this is called parallel transport. So I didn't talk about this, and this is also linked to these Christopher symbols and all that stuff. Okay, so in summary, manifolds are sets that are locally similar to Euclidean space. Manifolds generalize the idea of surfaces to abstract spaces. Every manifold has a tangent space at each point. The tangent spaces are vector spaces, very important to remember that. They generalize velocities to the case of curved surfaces, because velocities will always be in the tangent space, so always kind of get off of the manifold, like the vector brings us outside of the manifold. And a basis can be obtained by, I didn't talk about that, but by differentiating the local coordinate maps. Smooth manifolds can be defined intrinsically by defining an inner product on the tangent space called a Romanian metric. And this Romanian metric can always be obtained by the embedding into some Euclidean space and the pullback of the identity metric associated to Euclidean space. And geodesics are equivalent to straight lines on manifolds. Okay. Are there any questions?